Thank you all for coming to my talk. Thank you all for coming to RailsConf, and thank you, Megan, for the wonderful introduction. I'm sure a lot of y'all have done this. In fact, all of y'all might have done this. But how many know how to do this? By the end of this talk, hopefully all of you. Before we get too far in, I want to explain who I am. I'm Matt. Matt Duszynski has said. You can find me on Twitter. You can find me on GitHub. Please do. Fun fact, I can plug a USB cord in the right way around, first time, every time. That's not true, actually. How'd you go? And as Megan said, I work for a high-tech company in Southern California. We're possibly the highest tech company. And we are building the platform for the cannabis industry and the millions of cannabis users around the world. Sounds lofty. DHH might take me to task for that. But if that sounds interesting to you, definitely stop by the booth over in the exhibit hall and talk. You can't miss it. We're always hiring, and it's a damn fine place to work. If you just like having a good time and you're happy with your current job, stop by the booth anyway and RSVP for our party tonight, which is going to be awesome. I hope to see y'all there. So in my time at Weedmaps, I've been there for a little over a year and a half, and unfortunately, I have taken down production. Before I go into that, though, I want to do a quick audience participation, if I can see. Can y'all raise your hands if you use a relational database like PostGRES or MySQL as your primary data store? Well, you're going to talk about database migration, so I figured that was about what you'd expect. Second question, how many of y'all have tables with 1 million rows or more in that database? Okay, good, good. Then this talk is very applicable to y'all, because the sort of migrations that work pretty well for 50 records tends to not work so well for 50 million. Yikes. So for our first example, let's talk about something that I think you would consider pretty simple, adding a column to the database. Let's say we have our users table, we have our application, we've got millions and millions of people using it because we're a really successful startup. And we want to be able to mark a user account as active or inactive. I don't know how you got this many users without needing to mark them active, but bear with me for the sake of this example. Pretty simple database structure. We add a column, active, it's a Boolean, this is true, false. And we probably want to mark our existing users active so we don't lock everybody out of the system. So in order to do that, you might write a migration that looks something like this. Add column, users active, Boolean, default to true. This will get the job done, right? Wrong. No one can log in, no one can sign up, everyone is furious. Your app gets raked on Yahoo News. Your VCs get angry. It begins the downward spiral. Somehow a plane crashes into a mountain. We're not sure how that happened. But in order to understand what's going on here, we have to talk about what's going on under the hood with locks. Locks, there we go. Locks are the mechanism that your relational database uses to ensure that multiple operations don't update the same row at the same time. There are a lot of different lock modes, unfortunately too many to go into detail here, but to give you an idea, they range from an access share, which basically is the lowest level. I'm accessing data, but anyone else can access it too. I'm not doing anything dangerous. All the way up to access exclusive, which is no one else can do anything with this piece of data that I'm trying to access because I'm doing something that is potentially dangerous, like updating or deleting. It might change. When you're doing a database migration, even one as simple as the one we saw earlier, it will obtain an access exclusive lock on the table in question and prevent any other connections and the entire rest of your application from reading or writing data to that table until the migration is complete. So let's watch that in real time, real-ish time, with our example users table. You'll have to imagine the remaining 9.999 million users. I could only fit so many on this slide. But our migration begins running, and the first thing it's going to do is obtain that access exclusive lock. It's going to add the column. So far, so good. And then we're going to begin filling that column with active true so people can log in. So our little elephant here is PostGRES doing its thing. We've marked the first user, Alice, as active. Let's keep it going. So far, so good. We marked Bob active. Uh-oh. First problem. Alice is trying to log in, but she can't because the entire table is locked. Your application can't read data from it. And she's stuck there at a hung login screen or a 500 error, or she goes and uses your competitor's application. Overall, not good. Your migration's still running, though. Mark to the next column, true. Charlie's active now. Now Bob's trying to log in. Same problem. Can't do it, can't read the user data, can't log in. The migration is continuing to run, and users are continuing to try to log in, and you wind up with this pile up of queries that can't be responded to and this pile up of users that are very upset. The migration finally finishes running, releases that lock now that it's done filling all the data, and what you're left with is a cadre of dissatisfied customers. Probably not what you were planning on when you decided to mark users as active or inactive. So how do we avoid this? Well, don't do it, first of all. Don't add columns with the default value. That's a dangerous operation because of the locking mode it uses, and can and will cause downtime if you have enough rows in your database and enough traffic on your system. It is worth mentioning at this point that Postgres 11 actually addresses this particular problem in certain circumstances. Adding a static default value no longer requires obtaining a table-level access exclusive lock. But note the caveat under certain circumstances. There are other circumstances where adding a default value, for example, backfilling a new UUID column, will obtain that lock, and it will be a dangerous operation. Also, it's hard to stay up to date on that latest version. For example, we use Aurora at Weedmaps, and Aurora does not support Postgres 11. The highest version they have is 10.6. So you're at the behest of your database, your SaaS provider, your DBA, your ops team to be on the latest version to be able to take advantage of those new features, which you might not be. So general good practice, don't add columns with the default value. Sweet. We know what to do now. We're not going to add that column with the default value. Just get rid of that little bit right there. We're going to add it without a default value first. We're going to change the default once the column has been added. And then we're going to go back and update all of our users to mark them as active. And of course, we've split it into up and down because we're good Rails developers and our migration should be reversible. And we tested this in development and everything is hunky-dory. Nailed it. Not. So what's happening this time? Sorry, I just wanted to see that loop one more time. So what's happening this time? Now we got to talk about transactions. Transactions basically combine multiple database operations into a single all-or-nothing operation. Either all of your statements succeed within the transaction and it is committed, or something fails, violates an integrity constraint, whatever goes wrong, and the entire operation is rolled back. So transactions provide 4 guarantees: atomicity, consistency, isolation, and durability, which you might hear referred to by the acronym ACID. Check out our sister site, LSD Maps, to learn more. Not a real product. So this is a topic for a talk in and of itself, probably many talks, and we don't necessarily have to go into it in great depth here. Suffice it to say that the consistency and isolation that a transaction provides are guaranteed by locks. Specifically, consistency means that any operation will take your database from a valid state to another valid state. If you write a row, that row has to be valid in order to be saved and in order to be read by subsequent queries. Isolation guarantees that uncommitted transactions or uncommitted operations from one connection can't interfere with the operation of another connection. If the transaction hasn't been committed, that database hasn't made that consistent transition to a new state, and so other connections can't read the data. And there's some interesting stuff going on under the hood with tuples and indexing and multi-layer indexing, and again, not going to get into that right now. Come find me at the booth, because I would love to nerd out on database stuff with you, though. When a row is being updated, an exclusive lock is issued to prevent other people from updating that same row, which makes sense, right? If I've got some data to write, and you've got some data to write, and we try to do it at the same time, what's going to come out? Well, we don't know. That violates the consistency principle of relational databases, and so you cannot do that. Updates to rows are always made in a serial manner, and that serial order is guaranteed by locking within a transaction. Locks are issued on a first-come, first-served basis. They live for the duration of a transaction, even if the statement that requested the lock has already executed. So for most of your database operations, this might not be a very big problem, because they usually happen on the order of milliseconds. Where it does become a problem is, as you saw earlier, when you have to perform millions of database operations on a very large data set, it tends to take a long time. So how does this tie into migrations? Well, through a little bit of that Rails magic that we all know and love, everything you do in a migration is automatically wrapped inside a transaction. So, I bet you can imagine what this looks like, but fortunately you don't have to, because I have more mock tables. We're going to start after our column's been added and it's time to mark our users active again. Starting with row 1, we do not lock the entire table this time, because we're not adding a default value for the column, we're just individually updating all of our rows. However, in order to update a row, you have to obtain a lock on it. So we mark our first row as active, lock it, mark it active, true, move on. And even though that was successful, as I mentioned, that lock doesn't get released until your transaction can commit. And that can't happen until you update all of the rows, just like you wrote in the migration. So now we're on row 2. We obtain another lock for that row. We mark it as true. We keep going in this manner. And now Alice is trying to log in. And unfortunately, that row is locked, so we can't write data to it. Now Charlie's row is locked. Mark him active. One thing to note about this is that it is actually better than the first failure case that we described, because some of your users, those that haven't been updated to be marked as active, are not locked yet during this migration, and can log in successfully. So Doug is a happy user. And then he goes off on his merry way to use your application, none the wiser that there are any users experiencing issues. And now we move on to his row, and now more users are trying to log in. We lock that, and we mark it as true. And Doug is now active. Fortunately for him, he already logged in. And now our migration is done. All of the locks are released as the transaction is committed, and you're left with slightly fewer, but probably no less angry users. Again, not what you were intending to do. Now, if you were listening closely, you might have noticed I said can't write data because update locks don't prevent you from reading this previous value of the row until that transaction is committed and the value is updated. So when a user is logging in, we're just reading the password. We can read data. Why is this a problem? Are you sure you're not making updates when your user logs in? You might want to consider it. And even if this particularly contrived example doesn't necessarily apply to you, I'm sure there's a table in your application that you can't afford to block updates and write traffic to. For an e-commerce application, that might be your orders table. If you're a SaaS blogging service, that might be your posts table. There's always some reason for your application to be writing data. And while you can chance it, and maybe 2 unhappy users is an acceptable margin of error, it's better to just not backfill data inside a transaction. A lot of advice to just don't do it, right? If only everything was so easy. But hold on a second. We like transactions. They have all those nice ACID properties that we want when we're manipulating a database. We don't want to get into an inconsistent state. We don't want connections to start conflicting with each other. That makes for an unstable system, and that's just not going to work. So you'll notice it says, don't backfill data inside a transaction. What we're going to do is first pull this line out of the migration because we're inside a transaction. We like that. We want our column changes to happen in a safe manner. And we're going to write a completely separate migration to mark all of our users as active that runs after. The first line here that you see, disable DDL transaction, DDL, data description layer, disables that global transaction that I mentioned earlier. So it's implicitly enabled, but you do have the option to explicitly opt out of that behavior while you're running a particular migration. Then, within our up method, rather than marking every single user as active inside a transaction, which is dangerous, and rather than marking every single user as active outside of a transaction, which is dangerous for different reasons, what we're doing here is iterating through our users in batches and wrapping each individual batch inside of a transaction. Batch size defaults to 1,000. Of course, it's configurable based on your individual needs. But the key here is that this transaction that's updating 1,000 rows is going to complete and commit much faster than a transaction updating 10 million rows, orders of magnitudes faster, believe it or not. So that changes your lag time from minutes where your entire user base can't log in or use your software to the order of seconds or even less, while an individual subset of users might receive a slightly delayed response, which in almost all circumstances is an extremely, extremely good trade-off. And your users most likely won't even notice that anything happened. So our rule of thumb here is don't mix schema and data changes because you're going to wind up getting lumped in this transaction, and that's going to delay your updates, cause extensive locks to be held for long periods of time, and generally bottleneck your system at the database. Don't forget to put those updates back inside a transaction, just at a scale that works for you and works for your system and isn't going to block for extended periods of time. Now, we finally got our column added. We finally got all the values put into it. We only caused 2 production outages. Pretty good week, right? And now, we probably want to be able to look up which of our users are active or not. So we're going to add an index. You'll note that this says for Postgres only, and that's because the internal implementation of indexing in MySQL doesn't have this particular failure mode that we're about to discuss. Again, not going to talk about how different meta indexes point to different tuples, which point to actual disk locations. Suffice it to say that Postgres has a slightly more complex indexing strategy that has a particular edge case associated with it. So we have our very simple migration here. We're adding an index to the active column on users. Totally straightforward. Nothing could go wrong. Of course, you've been at this talk long enough to know that's not why I put that up on the screen. In addition to running that inside a transaction, adding an index in Postgres will, by default, obtain one of those nasty table-level locks that we described earlier while it reads all of the data in the table and writes it all to the index in one fell swoop. And just like you are locked from updating an individual row, while Postgres is trying to write an index, you can't make changes that would affect the way that index is written, such as updating a different row. And so basically, your database state is frozen by Postgres until the index is calculated and written, at which point you can then modify rows again. Fortunately, this is generally realized as a bad thing, even by the folks who maintain Postgres. And they added a very simple algorithm that can create a new index and write it to disk without blocking reads and writes. So in addition to disabling that transaction at the top, just like we talked about earlier, we're going to apply the algorithm concurrently to our index, which tells Postgres to add it in a non-blocking manner. Simplest thing in the world. Note, as I said, Postgres only. If you put algorithm concurrently on your migration and you're using MySQL, this will fail with an error. You won't break anything, but it won't work either, so don't try it. Or do try it. Your database. But whatever you do, do add Postgres indexes concurrently. It adds a little bit of overhead, but it avoids massive table-level locking that will generally cause problems with your application. All right. So now that we've talked about several potential failure modes and things that you shouldn't do, now it's time to talk about a time when I did those things that you shouldn't do. So, at Weedmaps, we have a pretty significant audit trail of operations that people are doing in the system. Makes sense, right? We want to know when people are logging in, who's making updates to what, compliance, security, general goodness. And what that looks like, at a very high level, is we write actual changes to the model to our main Postgres database, and then we write an audit record for whatever changed, what operation happened to create, update, or delete, and the properties of the model that were changed. And we write that to a separate database. You could easily write it to a separate table in the same database. That's an architecture decision based on the size of your data set and scaling needs. But I will say, I'm very excited for Rails 6 and the multi-DB support, because there's a lot of hackery that we had to do to make this work. But that's neither here nor there. The specific case that we were trying to address is that we needed to update a compound index on the audits table you haven't seen a compound index, it's same as a simple index, it's just on 2 columns. In this case, it was a polymorphic association, and we wanted to index on both the type and the ID column because that's how we're going to be querying. So what do? We drop the old index, we add the new index, concurrently, of course. No locks, no transactions, didn't make any obvious mistakes with the migration. What could possibly go wrong? A lot. Ultimately, we wound up taking down our entire production system for about 45 minutes, which is about 45 minutes in the middle of the afternoon as people are getting off work, as people are using our service to try to find cannabis. So bad time to have a massive production outage. But what happened? If we look at the migration, it looks pretty sane. We're not in a transaction. We're adding that index concurrently. What could possibly have gone wrong? Why did we take down production with this indexing change? And in order to know that, we have to talk about how concurrency works. Now, there's going to be some math on this next slide. That's the math. Don't worry, we'll walk through it. Little's law is a very simple equation that governs the relationship between concurrency, throughput, and response time, which ultimately controls how many requests your system and your application is able to handle within a given time frame. For example, if you have 100 requests per second, and you're averaging a 40 millisecond response for that request, for those requests, I should say, that means that at any given point in time, you have 4 requests being served by your application. This also works in reverse, where if you have 4 threads in Puma, and your average response time is 40 milliseconds, you can calculate and know that you can serve up to a theoretical maximum of 100 requests per second. Note the relationship between response time and concurrency here. If I add a 0 to your response time, you also wind up adding a 0 to your concurrent requests. And I don't know how many of y'all run 40 or more servers, but what I do know is that scaling up from 4 to 40 is not something that you can do very quickly and possibly won't expect to do at all. So, Little's law helps us determine the theoretical maximum level of concurrency that your application can support at any given time. If you use APM, if you've heard of Little's law before, if you've applied it to your own application, you might be thinking in terms of Rails requests and responses, but your database obeys the same principles. It's a service, it has a connection pool, it takes requests from your Rails app, and it generates responses in response. Where you can run into problems here is when requests start queuing because they arrive faster than your application or its database can respond to them. If a database operation blocks many requests for a long time, you'll wind up saturating your connection pool. You won't be able to access your database, first of all. Usually that causes problems for your application. So you probably won't be able to serve any requests, and the entire system will grind to a halt, probably at the worst possible time when you're at a conference and no one's on call. So, why was this a problem for our audits? Well, that's because we didn't understand what was happening when those audit records were being written. So now, an auditing overview, but accurate. First, we write the actual changes to the database. But second, we have a little tiny read query here just to see what version that record is at. So we're able to subsequently write the next version to the audit database. So rather than being a write-only append log that we thought we had, it turns out that every audited database operation was actually generating a read in addition to the write on that audits database. Rather than being 99% writes, unless a user happens to want to look at the audit trail for their listing, we were actually about half and half reads writes. And that causes problems because why do you index things? Fast reads. What did we do? We dropped an index. And that changed our query performance on the audit database from several milliseconds, generally acceptable, to several seconds, generally not acceptable. And if you remember the Little's Law multiplier earlier, that changed our level of concurrency slash the number of requests that we can handle by several orders of magnitude. So rather than being able to handle our 10,000 RPM production traffic at that particular time, we wound up with enough bandwidth to handle 10 RPM. So what that looks like with some more pretty animations is when we have our auto-scaling group, we have our multi-region AZ, cool stuff. This is true for a single deployment as well, but I figured I might as well give you an accurate representation of Weedmap stack. We have these different Rails applications talking to the database. And requests start coming in. They're trying to generate that audit trail as they've been programmed to do, but queries that were previously quite fast are now quite slow. And so once all of these requests come in, they're all trying to access that audit database. You wind up with your connection pool saturated, all waiting for a response from Postgres, and none of your applications can do anything else because all these requests are hung open waiting for a response from the database server. And then all the other requests come in and completely take everything down. Note that our particular example relates to our audits database and our audit trail, but you don't have to be writing an audit to be affected by this. Any long-running query can potentially saturate your database connection pool on any table at any time. And if that happens, all of your queries are going to be stuck waiting for those long-running queries to complete. So what do? You do test your database performance. You need to understand the performance characteristics of your application. You need to understand how they change during and after a migration. And you need to do this on a regular basis so you know what your application is doing. If we had identified the audit reads as a significant portion of our database traffic before that migration ran, we likely would not have written it and run it in the manner that we did. And even though query performance was fine before the migration, and it would have been fine after the migration once that concurrent index was re-added, so slow queries during the migration caused a cascading failure that took down our entire application. So let's talk about how you can do that. Little tools and resources to help keep your database healthy while still allowing you to make schema changes. First, a couple gems. There are some static analysis tools that will warn in advance about certain unsafe migrations, the things that I've covered here and the things that haven't been covered here, changing column type, dropping a column, adding a JSON column to a Postgres database. There's a lot of things that are unsafe that I just don't have time to cover. But in general, you want to catch problems at dev time, not deploy time. If you write safe migrations, you'll run safe migrations. So I advise checking out one of these two gems, strong migrations, zero downtime migrations, possibly check out both of them. They hook into the DB migrate rake task and will throw an error if your migration is written in an unsafe manner. Which one works better for you will likely depend on your specific database engine, version, schema, what you're doing. They don't exactly overlap. They both cover some slightly different things. And it's not technically a gem, but I did want to throw it in there that GitLab actually has a really, really cool, powerful migration helper system that they've built in that handles a lot of these things and more, which unfortunately is not abstracted out into a gem, so it's difficult to pull in and use in your own project, but it's still worth checking out because they give a very good detailed explanation of these things that I've talked about here as well. Second, APM. I think you could probably throw this slide in any talk about any application in any language, but understanding your performance is absolutely critical to understanding how migrations are going to change it. There are all sorts of options for this: New Relic, Skylight, Scout, AppSignal, many others. I hope all of you are using one already, but if not, maybe start by checking out the ones that sponsored this conference. But the most important tool in your toolbox is you. You, as the developer, are going to be your own best resource in not doing dangerous things. Static analysis can only go so far, and as we saw in the audits case study, you can take down your database in a manner that the software itself would be completely unable to detect because it doesn't know how your queries work and it doesn't know what the relative performance of them will be. You need to keep up with changes in your database engine, both knowing that there are changes, knowing what's in those changes, and keeping your database up to date. I wish we were on PostGRES 11, but we're not. Practice these things in a low-stakes environment. You don't want to have the first time you write a complicated, safe, multi-stage migration to be when you're running that migration on a multi-million row table in production. There's nothing specific or special about these techniques that don't apply to smaller tables. And I advise implementing this even in situations where you don't think you need it, because when you write safe migrations by default, you never have that cognitive overhead of, man, how big is my table? Does this one need to disable the transaction, or can I run it into the transaction? You don't want to spend time thinking about it. Just do it safely all the time, and you won't have to worry. It's always better to listen to that nagging little voice in your head. Did I do this right? Is this safe? Am I going to take down prod? I would always rather have someone prove that a migration is safe or challenge me to prove that a migration is safe than assume it's safe by default, right up until that little adrenaline hit or large adrenaline hit when all of your metrics go into the toilet on a deploy because you've got a bad migration running. Quick little recap. Commit this to your memory. Don't add columns with a default value. Don't backfill data inside a transaction. Use many smaller ones. Don't mix schema and data changes in the same migration because you wind up with that global transaction that you need to avoid. Do add your Postgres indexes concurrently, and do monitor and test your database performance before, during, and after migrations. Test all the friggin' time. And remember, uptime begins at home. Thank you.